Welcome to AxisVM. In this tutorial video, we will cover the dynamic analysis of a 4-story steel plane frame. This tutorial is described in more detail in a PDF guide available on the AxisVM website. In this example, the capabilities of the AxisVM dynamic module are introduced and a complete time history analysis is presented. Different types of dynamic loads are applied. 2 types of support accelerations are used. Induced vibration of a rotating machine is modeled by dynamic nodal loads, and the effect of a short-term shock load is examined. Linear elastic behavior is assumed. However, in the analysis, the second-order p-delta effect will be considered. In this tutorial, the creation of the finite element model will not be described. However, the model can be easily constructed by applying the knowledge of the previous tutorial examples. The starting file is also available for download on the AxisVM website. Once you are in AxisVM with the model opened, start by creating load combinations. Create load combinations for the vibration and dynamic analysis based on the static loads. In our task, the solution is complex because substantially different dynamic effects are examined in the same model. The vibration analysis will be executed in 2 different ways. In the case of a seismic sine wave excitation with a shock load, we will consider only the horizontal mass component because the applied dynamic load contains only horizontal components. In the case of the machine-induced vibration, the vertical component must also be taken into account. The same compilation of static loads will be applied for each dynamic load, but due to the considered mass components, the vibration analysis will be performed on different combinations. The reason for this is that the program binds the results of vibration analysis to the set load case and combination. If a new analysis based on the same load combination is run with different parameters, the previous results are not stored. Therefore, 2 different load combinations will be applied to store all the results of different analyses. Create 2 user-defined combinations with combination factors of 1 for each scenario. Before any analysis, the elements must be meshed to get smooth and correct results. Change to the Mesh tab and click on the Meshing of Line Elements icon. Select all the beam elements and set the mesh to divide each element into 4 segments. Now change to the Static tab. Perform a linear static analysis to check the load-bearing capacity of the frame under static loads. Now check the main results and make sure that there is no problems with the finite element model. In the next steps, the dynamic loads will be defined. Change to the Loads tab. Here, click on the Loads Group and Loads Cases icon. Beside the existing static load cases, create 4 dynamic loads. Click on the Dynamic Load icon and rename the new load cases as follows in the video. Firstly, a seismic type excitation will be defined. Select the EQ load case. We will use a support acceleration from an earthquake which is included in the database of the software. Click on the Dynamic Support Acceleration icon and select the nodal supports of the ground floor columns. In the window, define the global x-directional seismic acceleration. For the AX component, click on the Dynamic Load Library icon to load the specific function from the database. In the library, select the correct function and the earthquake diagram will be displayed on the right window. To recover the values recorded at the site of the earthquake, set the x-directional acceleration to 1 meters per second squared in the next window. Setting this constant allows the load factor function to be scaled without modifying the original dataset. Now change to the Sine load case and click on the Dynamic Support Acceleration icon. Select all the nodal supports again. For the AX component, click on the Function Editor icon. In the window, click the Formula icon and define the following sine wave. Using the formula, the software generates the discrete series considering the given time step and the duration of the excitation. Close the window by pressing OK and the dynamic load function editor will appear again. In the window, the specified function can be seen along with the data series of the curve considering the given time step. Close the editor and save the specified function with the name sine. In the window, set the acceleration constant value to 0.75. The applied dynamic loads are indicated by the arrows under the supports, and the values above them are the set constant acceleration values. Change to the machine load case to model the dynamic effects of rotating industrial machines. We will use a time-varying concentrated load to simulate the effect of rotating machines with simultaneous phase motion. Click on the nodal load icon and select the following nodes. The time-varying resultant force is modeled by its global x and z directional components. For this purpose, two dynamic load functions should be applied to describe the circular motion. For the x directional force, cosine is used, and in the z direction, sine is used. The time series to be applied starts by linearly increasing to a harmonic waveform and ends by linearly decreasing. The complete series was prepared in a Microsoft Excel spreadsheet because of its complexity. This dataset is in an enclosed Excel file. Specify the load factor functions of the F sub x and F sub y nodal forces one after another. Copy the generated data into the cells of the function editor. Take care to not copy the row of t equals 0 because the first row cannot be overwritten. Save the new functions with the name m cosine for the x direction and m sine for the z direction. Close the editor and then set the constant load to 7 kilonewtons for both components. Now close the window by pressing OK. The applied dynamic nodal loads are indicated by the arrows in the x and z directions under the supports. The values above them are the set constant load values. Increase the magnitude of the load in the middle. Click on the sign of the load and change the value of the Fx and Fz components to 10 kilonewtons. Finally, apply a short-term dynamic nodal load as a shock load in the shock load case. Click on the nodal load icon. Select the following nodes. The steps of the data input are similar to before. Firstly, the load factor function should be defined, then the value of the constant load should be set. For the Fx component, click on the function editor icon and define the load factor function according to the following data series. The data has to be entered step by inserting new data rows and entering the corresponding values. After finishing, set the Fx constant load to 10 kilonewtons and confirm the changes with OK. Change the value of Fx in the top and bottom nodes. Reduce the load in the bottom node by changing the value of Fx to 5 kilonewtons and increase the load in the top by changing Fx to 15 kilonewtons. Change to the Vibration tab and perform a vibration analysis to determine the lowest natural frequencies and mode shapes. In order to avoid a resonance effect, the natural frequencies must be compared with that of the different excitations. The Rayleigh damping constants in the dynamic analysis will also be tuned considering the dominant vibration shapes. Click on the vibration analysis icon. Firstly, the type of vibration analysis has to be selected. We will use a second-order analysis. This means that the solution includes the effect of axial forces of truss and beam elements on the system stiffness. In the vibration analysis, the masses can be converted by the loads defined in a load case or combination. We will run two different analyses based on the two load combinations. Select CO number 1 for the first analysis and CO number 2 for the second one. Set the number of maximum iterations to 30. In the first analysis, set the number of mode shapes to 12. Only the x-directional mass components are needed. Uncheck the others and then run the analysis. For the second analysis, in the second load combination, Set the number of mode shapes to 30. Also select both the X and Z directional mass components and then run the analysis. Let's compare the mode shapes for each analysis. The results of the analysis are nearly identical considering the x-directional shapes. The main vertical displacements appear only in the higher modes. Based on the results, only the first 5 shapes are dominant. Open the table browser to see the summarized data of the mode shapes and their modal mass factors. In the list on the left side, select the Frequencies option to display another type of summary table which contains the frequency, period, angular frequency, and relative error of each eigenvalue. In a time history analysis, the factors for the Rayleigh damping have to be set based on the main dominant frequencies. The constants will be tuned by considering a range of frequencies. The boundary values are the following in our cases. Based on the first analysis, the lowest frequency is 1.12 Hz and the maximum is 9.09 Hz. In the second analysis, the lowest frequency is the same and the maximum is 9.2 Hz. After the vibration analysis, change to the Dynamic tab. Click on the Dynamic Analysis icon and perform the necessary calculations for the 4 dynamic load cases considering the following settings. Along with the dynamic effect, apply a static load on the frame as well. Change to the load combination CO number 1. Now the specific dynamic load case has to be selected. When setting the time increment, the dynamic properties of the excitation and the response of the structure must be considered. It should be set depending on the highest frequency of the excitation. Note that increasing the time increment affects the quality and accuracy of the results. To check the response of the structure, select a typical node in the structure where a displacement is expected under the excitation. During the analysis, its displacement, acceleration, and velocity can be tracked. Set the direction field to X and select to track the top left node of the frame, which is node 17. For the seismic load, set the time increment to 0.02 seconds and the total time to 21 seconds. These values correspond to the load function of the excitation. Set the Rayleigh damping constants to A equals 0.6265 and B equals 0.0016 seconds. These values were calculated using the damping function and the minimum and maximum frequencies from the first vibration analysis. Enable the option to follow geometric nonlinearity of beams and make sure that the number of maximum iterations is 20. For the sine wave load, change the time increment to 0.01 seconds and the total time to 10 seconds, but keep the previous damping constants. However, for the machine-induced vibration load, change the time increment to 0.05 seconds and the total time to 25 seconds. For the shock load, change the time increment to 0.02 seconds and the total time to 20 seconds, but keep the previous damping constant. During the analysis, the results are calculated considering the set time interval, but the results that can be queried depend on the time interval of the saving. The results of each time step are put in separate cases denoting the time step, time, and the load case of the result. In dynamic tests, the result components are supplemented with speed and acceleration data of the nodes. A specific time step can be selected from the drop-down list. Note that each dynamic time step contains the results of the combined effect of the set static and the dynamic load cases. An animation can be made to present the dynamic results. Select the EQ load case and the EX result component and click on the animation icon. The video parameters can be set by clicking on the Setup icon in the lower corner. With the slider at the bottom, the speed of the animation can be adjusted. If the result display is also switched on, then results are also shown in the animation. Generation of the phases can be started by clicking on the play icon in the bottom left corner. If the video frames have been completed, then the animation can be saved. To maximize the resolution of the animation, maximize the size of the animation window. Creating diagrams can be helpful in evaluating dynamic results. The results can be displayed as a function of multiple components, and two types of graphs can be presented at the same time. For the EQ load case, click on the diagram display icon. By default, the diagram will display the increment versus time curve. Click on the diagram parameters icon. First, let's display a single curve, the acceleration curve of node 1, which is a support, as a function of time. Select time for the x1 component and AX, which is the horizontal global x-directional acceleration, for the y1 component. Click on the node button, and in the main window, select node 1, which is the bottom left support. Then close the window with OK. Under the graph, there is a scale which represents the time axis, and it contains green and black markers at the ends. Moving the black marker along the axis will show the current result value on the diagram based on its position. Moving the green markers allows the range of the displayed function to be set. If the range of the diagram has been limited by the green markers, then the graph can be stretched by clicking on the Fit in View in X direction icon. The results of the calculated time steps can be presented in a table. Click on the table icon and a table appears next to the graph, which contains all of the data. Now let's show the my flexural moment of beam number 27 in node 5 as a function of time. Click on the diagram parameters icon. On the diagram, select time for the x1 component and select my for the y1 component. Then select the corresponding node, number 5, and the beam, number 27, by clicking on the element button. Select the node, and one of the beams which belongs to the selected node will be highlighted automatically. Press Tab to cycle between the beams and then select beam number 27. Click on the node again to close the selection. Then click OK to accept the changes, and the required curve will be presented in the diagram display window. Drag the green markers to the ends to display the whole diagram. Now let's show the displacement of node 1, a support node, and node 17, a top node, as a function of time on the same diagram to see the relative displacement between the nodes. Click on the diagram parameters icon. On the first diagram, select time for the x1 component and EX for y1, then select the support node. Activate the second diagram with its checkbox. Keep the x2 component as time, but change the y2 component to EX. Then select the top node, node 17. Both displacement curves will be displayed in the window. The blue curve shows the displacement of node 1, and the red curve belongs to node 17. The program uses different scales on the vertical axes, but the same scale can be set by clicking on the same range icon. For any specific position, the relative displacement can be calculated by taking the difference between the two curves. Please see the user's manual for more features. Close the window by clicking on the OK button. Next, we'll follow the motion of one of the excited nodes in the machine load case. Change to the first time step of the machine load case. Click on the diagram display icon. Then click on the diagram parameters icon. Set the x1 component to EX and the y1 component to EZ. Only one diagram is needed, so uncheck the second diagram and then select the following node on the first level. Due to the excitation and the movement of the structure, a quasi-steady movement similar to an ellipse is formed. Now analyze the displacement of node 17 in a diagram with the same settings as before. Limit the range of the curve to see two internal waves. Adjust the markers to 5.35 seconds and 8 seconds. In this example, a quasi-harmonic motion is induced by the excitation. If the time increment or the density of the saved steps is insufficient, then the curve will be piecewise and the accuracy of the solution will not be adequate. The load function used was defined in 0.01 second time steps, but the calculation was performed and the results were saved considering 0.05 second time steps. The appropriateness of the applied time step can be checked by analyzing the result curves by counting the intermediate points of a wave. Finally, let's analyze the damping effect of the frame examined in the shock load case. Select the first time step of the shock load case and return to the diagram display parameters window. Set the displacement of node 17 to display as a function of time as follows. In many cases, it is needed to evaluate the results of various dynamic loads together using envelopes. Present S-min-max results are an envelope of the machine and shock load case results. Create a new envelope. Click on the Result Display Parameters icon, and in the window, click on the Envelope tab. Create a new envelope and rename it Custom. By default, the new envelope will contain all available load groups and cases. Change this by keeping only the machine and shock load groups. Also, make sure the display shape is undeformed. In the main window, find the new envelope, Custom, in the drop-down list and select the Min-Max envelope. From the drop-down list of results, select S-Min-Max under the beam stresses components and change the display mode to filled diagram. By querying any result component, the envelope result of the set load groups or load cases can be seen in the window. Click on one of the beams to display the cross-section beam stresses. The results for any load case and time step can be displayed. The left figures show the stress results along the axis of the beam considering the current time step. The middle shows the different stress diagrams of the selected cross-section and their main values, and the table on the right shows the stresses in the calculated points. The stress results of any cross-section along the beam can be queried by dragging the vertical axis of the figures to the desired position. In the lower right corner, the current position can be controlled by overwriting the current value or by dragging the vertical axis to a particular position. Thank you for watching. Please visit the AxisVM website for a detailed, in-depth PDF guide to this tutorial, as well as additional information and tutorial guides.